Today we'll be discussing linear regression and ARDL on Python. First step first, we essentially download Python, of course, from their official website. Then in order to communicate with Python, we download a Jupyter Notebook, also from their official website. Then to make things easier, we download Anaconda, which essentially includes the Panda software, which lets us enter data in the Python. Then we use NumPy for data analysis as well. We also download that. That actually, when you download Anaconda, these two packages actually are included in that download. After that, you then have to download different sub programs like Matplotlib, which is for graphs, Seaborn, Arch, Stats Model, also for analysis. Then comes the part where you actually enter the data in Python. Different people have been using different commands online. Um, there's this df command where df is the data file, which says like pd dot read underscore excel. This is for excel, xls or xlsx file, and this one is an older version of excel files, and this is a newer version, so mostly these files are used. And after writing this particular command in Python, you then give the file destination to the software like Jupyter Notebook, then the file's name, and then the extension, which may be .xls or xlsx. Then you write in print df. Um, there is also another way of doing it, where for instance you're using a .csv file. So then you can just simply write import csv data is equals to open the file destination and that name, um, and then the csv reader and print data. Or you can simply use the request option, where you just have to enter one particular command, not steps of different commands, but just one line of command is used for that. There's also another way where you can use the open method. Just simply write open and then open file, or you can use the url underscore downloads command, which is mostly for files that are actually available online. So you can use their url, give information about that to Python, and then use the file. Before getting started, of course, we need to make sure that the data is stationary or not stationary. We need to have that information with us. So a simple way of checking the stationarity is by looking at the plot of the data. If the data tends to move away from its mean, it is said to be non-stationary, as we all know. Another method is to use the augmented Dickey-Fuller method, or of testing the non-stationarity, and where the unit root exists is the null hypothesis, and alternate hypothesis essentially says that unit root does not exist, which implies that the data is stationary. As I said, this is a non-stationary test, so alternate hypothesis is stationarity. To start off with the very simple basic linear regression on Python, these simple commands are used. Lindreg, linear regression, where you can get the linear regression coefficient, and then there's the other one, lindreg.intercept, where you can get the information about the intercept. So a very easy way of another very easy way of importing data into your Python is to simply get it from Excel. So let's open Python. We select Python file from here. Okay, to start off, we essentially import, like I mentioned earlier, NumPy, Matplotlib, and all these things. So, and we press Shift and Enter to run it, or you can simply use this Run button. Then to um, include the variables in this particular regression, say we have x and y um, with the following values: x from 1 to 10, all that, and then y from 3 to 60. Now we can simply enter this information into Python by copying it from the Excel data file, or we here have to use the transpose option if the data is vertical, and then we transpose it, get the horizontal version of it, then we copy it, and if there are like um, see, I'll show you. See if there are like arrows present here, we simply backspace them, replace them with commas, and we put them in the array command, which is a numpy array command, as I've done here, and we run it. Then we tell our Python about the linear regression that we're going to run. And say we want to actually modify our x variable. So we can simply do it by using the reshape command. Shape. And so now our x is modified. Okay, so now we're like setting the ground for our linear regression. So we need to like so now it knows that linreg is essentially our linear regression command. Now we have modified our x, and now whatever value we will get from this particular x in our equation would essentially be a predicted value of y, see, in our regression. So we can call it y predicted. We are basically predicting our y using the value of x, of course. Now, in order to see this particular um, predicted trend of y variable, we're going to use a plot. And so we use a, very commonly we use a scatter plot. So we'll use a scatter plot here. Okay. And in order to tell, like, give more information about this particular plot to Python, we're going to tell it to make the line red, x and y just by predicting then y predicted, and we want the color of our line to be, say, red. Let me put this in uh, commas. Everything looks in order, and of course we wanted to essentially show us the plot that we're making. So okay, here we have it. Now this line particularly shows that like this is the linear line, and our predicted values of y are quite close to this particular linear line. Now say we were to like say this is our equation. Let's suppose y is equals to mx plus c. Write it here. Say this is y is equals to mx plus c, where y is our variable, that we're dependent variable, x is our independent variable, m is the coefficient, and c is the intercept. So in order to get the value for this particular m here, we're going to ask Python to give us the value of the coefficient. In order to do that, we're going to try to print essentially shows everything that we write or do in the sheet over here. If you don't ask the Jupyter or Python to actually print or show us what we're doing, we won't actually be able to see anything. So print option allows us to see what we're doing. So let's actually uh, check the value of our coefficient. Hmm. Just a second. Okay, so we write coefficient with a single f here. So if we write coefficient, like short for coefficient, we get the value 2 here. Yeah. And similarly, to get the value of intercept, oh sorry, yeah, we put underscore here. So we get this. Now we put these this value of intercept and this coefficient value in our equation, we get this. Yeah. Or simply can write here y, our y dependent variable is equals to 2, right? So or we can write the intercept first if like we usually do. So 18.7 our intercept or c plus positive relation, so 2 and x. So essentially we're saying that if x increases by 1 unit, y would increase by 2 units. So that is that. And if of course x is 0, so the intercept would be this, y would be this. After seeing how linear regression works on Python, we then move to autoregressive models. Autoregression is a time series model that uses observations from previous time steps as input into a regression equation to predict the value at the next time step. It is a very simple idea that can result in accurate forecast on a range of time series problems. As also, this is termed as regression of self because a variable is essentially tested on its own lags. So, because the past values of dependent variable are used as independent variables, here you can see that this is y, and this is the slope coefficient, and a lag of y, and then another lag of y is used. So in Python, we can simply start by importing all the important softwares, then loading the data set, then we split the data set, then then we can use a train auto regression system, and through that we can make certain predictions, and then of course print the results. In the results section, we get the value of the coefficients, then we get the predicted values, then we get the expected values, and the predicted values are shown in the with the red line on the plot. As far as the predicted values, they are shown with the blue line. So predicted values are essentially the ones that we are more interested in. Then another like autoregressive model essentially it's like most practically used autoregressive model is the autoregressive distributive lag model. In this particular model, the lags of even the dependent variables are used here, and essentially, when the variables under study are not all integrated at the same level, we make use of the ARDL approach. So, and most of the time, a researcher is faced with a problem of a combination of I naught and I one when he or she decides to opt for ARDL model. So, the ARDL provides information regarding short and long run relations. A particular command, which is known as dlagm command, is essentially an RStudio command, and people most commonly use ARDL on Python with combination of this RStudio dlagm command. Um, Co-integration is a preferred step for modeling empirically meaningful relationships of difference stationary process DSP, essentially where difference makes the variables stationary. So co-integration is concerned with the analysis of long-run relations between integrated variables and the reparametrizing the relationship between the considered variables into a into an error correction model. So essentially, we redefine our model through this particular method. Although ARDL co-integration technique does not require pre-testing for unit roots, it is usually done to avoid ARDL model crash in the presence of an integrated stochastic trend of I2. Essentially, like when the variables are integrated for order 2, ARDL is quite likely to crash. Therefore, it is best to actually test the integration order of the variables. Now, say we have an example case here where Y is the capital of a company, say company B, and X essentially measures the oil prices. So let's open our Jupyter notebook. We open Python 3. Now, here you can, I'll zoom in a bit. So here, the hashtag, the statements with the hashtag are not actually run, so we can simply just ignore those, doesn't matter. And if you have to enter, then to enter the data, simply start here. Now, essentially, this particular data file is available online. So we're essentially trying to read the data from a URL, this particular data source. And this allows us to actually look at our data a little bit. So here we have the, like I said, the capital and the price, oil price. Now, in order to look at our values in a graphical form, as we always like to do, so here are the values, and there are a lot of oscillations here and a lot of oscillations present here, though they are not exactly converging. No, kind of, they are converging to the mean. Then to run an OLS regression, essentially to see how the different lags of variables actually impact the dependent variable, different lags are taken. So here is this particular example. Lag of X are actually taken because oil prices, as X is oil prices indicator. So oil prices, they lay an impact on current capital of the company with lags. So essentially, like this particular year's oil price may have a continuous impact on the capital of a company. So we essentially take lag of X. Now we've told Python that we're going to take lag. Let's actually run the OLS here. We're taking 4 lags of price. Prices are X, like as I mentioned earlier. So price 0, price 1, price second lag of price number 3, then a fourth lag of price, and then yes, shift enter again. Hmm. Okay, so here are the results, the OLS regression results. And here we can see that the p-values for the first 3 lags. The p-value for the first 3 lags are actually significant, but for the fourth lag, uh, it is not significant. So we can actually try and run the OLS regression again with only 3 lags. This time we use just 3 lags. Okay. So now you know the first three lags are actually um, hmm. So here then this means that the oil price essentially affects the capital of the firm. Okay, so like we said that the third lag is actually significant to that the third lag of oil prices actually affects the capital of the firm, and so we can actually use these coefficient values and put them in our equation like here. For example, this is the capital of the firm, and this is the intercept, the price at time period t, then price with a lag of 1, and then 2, and then like that. So and essentially we conclude that the third lag of the variable of the price variable does indeed belong to the distributed lag model. So so the lag length we select for this model, Q3 is the lag length we select the model. Now moving ahead, after the OLS equation, as we've seen the requirement for lag selection, as well as we've seen how we can actually interpret the equation. Of course, when the coefficients are written in equation form, it is easy to interpret them. For instance, we can say that 1 unit increase in price would actually decrease the capital of the firm by these many units, which was also this is actually in dollars. So like these many dollars. Um, so like that's in here, okay. And an immediate reduction in the market capitalization of 125 900 dollars, keeping everything constant, and then a further reduction because of the lag effect 1 month later. So in an equation form, it is easy to actually interpret the results. So we do that, and we selected the model lags. As for the error correction model, so essentially ARDL approach, or the autoregressive or ARDL or ARD. So some people call it like ADL, some people call it ARDL. Essentially, it's the same thing as far as I know, and it's autoregressive distributive lag model. So autoregressive distributive lag model essentially is used uh, to in the ARDL in the error correction model. And here, when this particular model, for example, a change in yt with an intercept, and then the coefficient of its lag, of course, with the parameter, um, and multiple lags are taken. Then the independent variable x, of course, these are also independent here, but and so that different independent variables may be added. So when this kind of a model is used in an error correction model, a lambda term is essentially added. A lambda term is added, and this lambda term essentially is a coefficient of a another additional error term, and this has to be negative for the model to be actually in equilibrium or a stable model. So before this regression model, a simple model without lags is run first, and then information about the residuals is saved. I'll show you. So first, like the long run equilibrium model is run, like as mentioned here, where a simple model is run without lags. So here there are no lags involved. Here there are no lags involved, and then the other model that we already mentioned here is run. So we take an example where Q is the demand for food and X is the total expenditure. So essentially, we start by um, running this particular model where again we have taken data from an online source and put that in, which is CSV file. So we put that in your Jupyter notebook for Python to read, and then we want to actually get the idea about the data that we're using. So we go to Python, we paste all of this here, where like different columns of here and all the data that we've already discussed, expenditure and everything is actually here. We run it and we get these kinds of graphs. None of these graphs show a convergence, and these values can be seen down here. Let me just 1 second. So these values can be seen here. In the time period chosen from 1965 to 1990, none of these actually convert back to their mean values. In order to, like I mentioned earlier, here, 1 second, like I mentioned earlier, that before actually running our main model with the lambda in it, we actually just simply run a simple regression. So we do that by say defining our CI, which is our residual, and because we want information about a residual term, so we run this particular thing here, and so what we're doing here is we're basically running an OLS, and we use these to actually put the data inside it. Shift plus enter, and we have a problem. Okay, so here we have the value for. Okay, so this essentially is our residual term. After getting this particular term, we move forward with our main model, and this actually can be termed as our exponential elasticity, because as we mentioned earlier, x is our total expenditure. So there we go. So we then essentially we use the residuals of the co-integration equation C1. This is our C1, and create a regression model. Now, in this particular regression model, we have the lambda and the error term that we talked about on our earlier slide. So, how do we go about it? We add the residuals to the data frame. Then, what we do is we use this particular data frame and the residual and use this Bayesian form here to define this particular index here. So true or false options are essentially added in Python through the Bayesian function. Rather, but just you actually say that the Bayesian essentially is being used in the background to use these true and false options. So we make use of that, and then we use these the data in our particular columns, and we create the co-integration model. Now here, model number 1, it is created through our statsmod function that we earlier installed. SMF is short for that, as we defined in our earlier, like in our notebook. Then we use the OLS, and we make our formula here. And of course, we don't use the print option, we won't get actually any result. So in our result, we want the t values here, and we want the p values, and of course the coefficient value. So in our result here, all the values are significant. Also that the error term essentially has a negative sign, and as we mentioned earlier, the error term has to be negative for us to actually proceed with the analysis. Otherwise, we can't. And as it says here, that the p-value is quite acceptable. It's a good p-value. So essentially, we can improve the model by including, other variables which have an which are stationary at the order of I1. Log differences of relative food prices P over G divided here. So the model now becomes this because this particular portion is added here. So in model number 2, this is essentially just like an additional exercise. You can modify your model as whichever way you want. So here's this. So in model number 2, we've actually added the relative food prices P over G. And now one of the in fact two have become insignificant. So we now after deleting the insignificant terms, we can do that if you want. So after deleting insignificant terms, um, we already know the criteria. So we get to our final error correction model, and as we saw up here. So x over g was insignificant, but that is still here. So after tinkering a bit, yeah, this one is still insignificant. So essentially, the results that we get here with our SMF based OLS regression are short run results. So the coefficient values that are presented here are basically for the short run effects of the independent variable on the dependent variable. So here the short run demand elasticities with respect to the total real expenditure and the relative price are 0.3658 and minus 0.3236 respectively. So, like I mentioned earlier, so short-run effects are given in this particular table, where the demand elasticities with respect to the real expenditure, essentially the linkage is given, which is positive, and then another linkage is given, which is of relative prices, P as we defined earlier as price, and that one is negative. As far as the long run effect is concerned, that we saw earlier in our residual model. So that one essentially says that the expenditure elasticity falls slightly to 0.3554 in the equilibrium relationship, and that one can be seen in the first table that we actually ran. So this one here. And if needed, one can also see that the error term is white noise or not. So that is all about the error correction model using the autoregressive distributive lag model. So to basically conclude, Python, unlike R, does not have a built-in command for ARDL. Like for instance, a bounce testing ARDL method or something. So, like I mentioned earlier, R has a built-in command which is called dlagm, but Python lacks in that particular department. As for the ARDL through ECM method, error correction method is concerned, that we've just saw through, and that can be done through these stats model package. Um, and that does give a short and long term estimates. As for the stats model package, we did install that. I'll just go back to that here. We did install the stats model package, and that is the particular software that we use for the OLS estimation. OLS.smf. Use the correct down here. So essentially, ARDL then gives the short run as well as long-term results on Python using ECM, which is our error correction model. So SMF, then you form the formula. So in this particular model, we can then use ARDL on Python. Otherwise, R is recommended. As for the um, as for the feasibility of this Python, I've consulted a lot of online forums, and I've seen a lot in some articles in even. In fact, the one I quoted here um, with that particular name, it was here or here, Dirham or something. So yeah, I even quoted an article here, and that particular person also suggests that R essentially is this one, the Miran, I guess this one. So that is essentially more widely accepted for running or testing an autoregressive distributive lag model, and because Python essentially has lesser options available, even for lag length selection criteria, OLS mostly is used. So for ECM, it's good enough, but not for the but not for generally not generally accepted or very popular. All in all, ARDL is a very popular method because it um, uh, essentially it like kind of allows a researcher to actually go past one's restrictions. For instance, one has some variables and which like some are integrated of order 0, some are integrated of order 1. So essentially that is a problem. So ARDL is known to be like the best software that was produced in the 20th century because it allows us to actually move past that hurdle. We can actually use that to even when there is a combination of integrate variables available. Limitation, however, is that when the variable is integrated of order 2, then ARDL is known to crash down. So that is a limitation. Other than that, ARDL is very much accepted and quite popular. As for that, yes. Thank you very much. I'll conclude my presentation here.